Hi, folks. Welcome to another episode of YFTT, Yugabyte Friday Tech Talks. I have with me Brett. But before we get started, you can feel free to ask any questions. We're usually very interactive. Just drop a question in the comments box. Today, it's about how we generate how the database auto-generates IDs when you insert rows. But before jumping into the topic, Brett, do you want to quickly introduce yourself?
Sure, yeah. My name is Brett Hoyer. I'm working at Yugabyte since the spring now of 2022 on the developer relations team. So I'm working primarily with JavaScript technologies to develop distributed applications that leverage the functionality of the database and sort of educate the community on making the switch from a monolithic Postgres deployment to a distributed SQL Postgres deployment.
Awesome. Fantastic. Fantastic. Can't wait to get started. So tell us, Brett, why do we have to care about auto ID generation in PostgreSQL and Yugabyte?
Well, you don't have to care, but you should probably care, because based on how you choose to strategize your ID generation, this can have an impact on the latencies in your application, as well as some other things that we'll get into as far as security and other things. But for the most part, latency will be of primary concern in framing this discussion. Also, it's worth noting that there is not one size fits all solution, because there's so many different types of applications and database deployments that we're going to just frame the discussion so that you can make an informed decision based on your own application.
Awesome. All right. So let's get started. What do you have for us?
Let's do it. So in moving through these slides, I'm going to try to work relatively quickly so that we can touch on each of these strategies and then get to a quick demo that is backed by YBM, YugabyteDB Managed, which is our managed solution. And I have a cluster running there that I'm going to use for a demonstration. But the four strategies that we're going to discuss are auto-incrementing, sequence caching, client-side management, and UUID generation. So the first three are making use of a sequence in Postgres. And I think many people are probably familiar with an auto-incrementing ID field. And some might not be as familiar with UUID generation. And this can be a really powerful strategy when working with a distributed database. So we will be getting into that later on. So an auto-incrementing strategy is what most people are probably familiar with when you're working with a single node Postgres database. In creating a serial ID field, under the hood, Postgres is creating a sequence, which is then used on inserts to retrieve the next value from that sequence. So by default, our sequence is created. It starts at 1, it increments by 1, and on all of our writes, they will be ID'd sequentially. First write will be ID 1, 2, 3, and so forth. And by using a serial field, this sequence is owned by the user's table in this example, such that if we drop the table, the sequence associated is also dropped. So let's get into some pros and cons of this option. One of the pros is that this is just extremely developer friendly. Like, everyone can very easily wrap their head around this. If you're working on an API, you understand that when you insert a record, the ID will be of ID 1 and 2 and so forth. And people seem to enjoy the fact that this is sequential and easy to understand. Sequences are also atomic, which means that if we have multiple connections to our database, we can guarantee that the next value in our sequence will be unique between between these connections. The storage size is also relatively small compared to UUIDs when using an auto-incrementing field, because under the hood, this is an integer. So we can use small serial for a small int, serial for an int, or big serial for a big int with 2, 4, or 8 bytes accordingly. And the difference between these is how many records we'll be able to store in this table. And this decision can be made based on how many records you're planning on having in your database. And this auto-incrementing approach, I have shown it using a serial type, which then becomes an integer. But this can also be achieved using an identity column in Postgres. So some of the cons for this, especially in a distributed SQL context, we have to make an extra round trip to obtain the next value from our sequence on our writes. And that can be very costly, as we will show later on. This can also cause security vulnerabilities, in the sense that if you have a hole in your system, users will very easily be able to predict the next value in the sequence and potentially modify records in your system if you're not careful. This can also happen in development as well. And if you're importing data or merging data from various sources, you can have an ID conflict because of the fact that these are not randomly generated. So that can cause some difficulties. So basically what I'm saying is, the fact that it's sequential is both a pro and a con based on how you view it.
I think also, there's an interesting point here also, right? Like, can users rely on the sequentiality, even in the case of a single, like if let's say you try to do an insert and the insert fails for whatever reason, like I inserted row 1, row 2, and then my row 3 insert failed. Would the next row get 3 or would it be 4?
It will be 4.
It'll skip, right? So the sequentiality is not a guarantee, it's a best effort. Right?
Exactly. It's a best effort, and that's part of the cons in some of our future strategies, that we can have gaps in our sequence. So although it's sequential, it's almost a misnomer at some points, as you've mentioned.
Yeah. And Venkata has a question, which is, can you elaborate on how you make sequences atomic? Do you have some centralized server that generates these sequences numbers per table/relation?
So as we saw when we create the serial data type we use the serial data type under the hood, Postgres is creating a sequence which is tied to that table. So even in a distributed database, all requests will be going to that sequence to get the next value from the sequence. So we will never get a repeat in that sequence. I hope that answers the question. Do you have anything to elaborate there, Karthik?
No, I think you got it right. So the sequence itself is an object. That object itself is replicated, and there's a leader elected for that object, and that leader is the one that essentially issues the sequence IDs, right? So effectively, It is a centralized server, but it's not. It's still a highly available system, but it's a single one that issues it by default.
Yep.
I guess, which is why the con, right?
Exactly. All right, so the next two approaches will sort of build on our understanding of using a sequence and how we can improve upon that. So in using a sequence, we can introduce a cache, which caches a certain set of values from that sequence in memory on a per session basis. So that reduces the need for us to continuously query our sequence object for the next value in the sequence. So I'm just going to run through this as quickly as possible. So assuming that we have 2 database sessions, if database session 1 connects first, it will be allotted the first 100 values in our sequence, and session 2 will be allotted the next 100 values in our sequence. Even if session 1 and session 2 make writes immediately after one another in the beginning, this next write will have an ID of 101, not 2, because 100 values have been allotted to the cache for this session. So that is something that can be a little bit confusing to people as well, because although writes might be coming in from different sessions, the IDs aren't necessarily mapped to time. So that is something to note. And if database session 2 uses up its cache and does another write, it will get values 201 through 300, and session 1 then on its next write will update its cache and start at 301. So that is how caching works. And by default, Yugabyte uses a cache size of 100 on all of its nodes to benefit from this cache to improve latencies. And it could be a good idea to even increase this value if there are no memory constraints on your nodes. So the pros of this are that the values are cached in memory to improve latencies. Pretty easy to understand. And the cons are that you can have gaps in your sequence during dropped sessions, transaction rollbacks, and database shutdowns. So this too, like Karthik mentioned, can happen with just a default sequence, but it's often seen if you have a huge cache size, you could too have a huge cache in your sequence, or excuse me, huge gap in your sequence. So I'm going to go, do you have any follow-up on that?
No, I think this is good. I think, yeah, it totally makes sense. Yeah. So
I'm just going to run through this one fairly quickly because just in the interest of time. So approach 3 is client-side ID management. So we can use our sequence with an increment by value such that we know for sure that we can increment our IDs client-side and send those IDs from our client to our database. So our database is only using its sequence to update the client's cache, essentially. And for some use cases, it is nice to generate your IDs client-side if you're worried about offline use or dropping connections. There could be some value in caching certain things client-side. But this is a little bit of a niche use case, so I'm not going to go over this too much, but you could imagine querying directly for the next value and then automatically incrementing in your code. In this case, this is Node.js sort of pseudocode. And once we've used up all of the values in our incremented sequence, we would then query again to get the next value in our sequence and so forth. So that is an option. And values can be prefetched from the sequence to improve performance. In this case, you could say, I only have so many more IDs left, and you could make another request to get additional values. And this can have gaps in the sequence if your application fails. And of course, one major downside of this is there is additional application overhead and complexity for doing this.
Yeah.
All right. So we're out of the sequence land and into UUIDs, which are particularly interesting in the scope of distributed databases and distributed SQL. So UUIDs are not an integer-based data type. UUIDs are their own data type in Postgres, as well as Yugabyte being Postgres compliant, which is comprised of hexadecimal characters in a very randomized fashion. So Postgres has a built-in function for generating UUIDs, and there are also additional modules to generate other types of UUIDs if required by your application. but these UUIDs are generated algorithmically such that they're considered to be entirely random. Of course, there is a very, very small probability that you could generate that the same algorithm could generate this exact same ID, but you're generally guaranteed that this ID will not only be unique within the table that you are working, but also you might be able to have unique IDs across all of the tables in your entire data tier, which can be of value. So these can be generated either client-side or server-side as well, because we don't need to rely upon a sequence value that we're querying. We can run a function directly on the nodes of our database, or we can also use a library to generate UUIDs client-side and send these directly in our writes. So this is how we would create a table using a UUID data type and the gen_random UUID function. So on writes, we would call this function and write to a database. So the pros of this are that they're non-sequential, which we've already discussed the downsides of sequential ID columns. Can be generated on the database side or the client side. They're decentralized, so that can improve latencies. We don't need to continue pinging for the next value in a sequence. And it's easier to handle data import than in sequential systems, because we generally won't have any clash of our IDs. So if we're importing data from multiple sources, this can be of value to us. A con would be that the storage size is significantly larger for a UUID than an integer, typically 16 bytes as opposed to 4 bytes. Algorithms take time. This doesn't come entirely for free from a compute standpoint, and uniqueness is not 100% guaranteed, but it is by all intents and purposes. All right, so now we can get into our demo. There are a few things that I wanted to discuss prior to getting into the demo, but I'm going to go over 2 of these strategies that we've reviewed here. So I will get back to this slide. So the 2 strategies that I would like to show you are the sequence caching, which is, as I said, by default in Yugabyte, we set the cache value to 100 to improve latencies. This can also be increased. And I'm going to show a UUID example as well. But in order to facilitate this demo, I've created a 3-node cluster that is replicated across regions synchronously. So I will show that.
Got it. And you're doing this primarily because you want to show the latency of the operation, and that's really exacerbated in the multi-region deployment, right?
Exactly. I would like, and there are many ways to tune your database to improve latencies. We have many options here for your topology. And when you're planning to move from Postgres to distributed SQL, I would encourage anyone to look into the different topologies that we offer based on the needs of your application. But what we are concerned with today in this demonstration is the replication across regions, which can have high latencies if we need to reach a consensus between faraway nodes. So that is something that we will be going over. But again, there are different strategies to reduce those latencies. And this example is, as you said, I chose nodes that are very far from one another to show the cost in regards to latency. So to go over this deployment, I just wanted to show quickly in the YugabyteDB managed console what I've deployed so that we can run this simulation. So I've created a 3-node cluster that is replicated across regions. with a preferred region in Los Angeles. So there was a really great Friday Tech Talk on this channel back in December by Hari Krishna Sundar, where he went into preferred regions, and I would really recommend people to look into that talk to learn about some of the benefits. But in this case, the preferred region means that all of our reads and writes will be coming from Los Angeles. So even if we are connecting to a node in a faraway region, this connection will inevitably forward the request to the node here in Los Angeles. So that is the infrastructure that we are working with on the database side. And then I'll just show quickly this application that I've put together. It's really just a very simple node script where I'm connecting to this database, and I'm going to show both sequential and UUID use cases to show the difference between these two. And I'm just going to be inserting a bunch of records into this database so that we can see, using explain analyze, so that we can see what is happening in our database as we are making these inserts. So that is what we have here. And then I'm just going to run this script. So what I'm doing here is connecting to our node in the US East region. So that is not our preferred region. This is assuming that we are receiving writes from, a quote unquote faraway region. And that is further going to show the problem with needing to continuously get the next value from our sequence. So let's run this, and it will take a little bit of time. We're going to connect, and we're going to drop the existing table and recreate it. And then we will be able to write records, and we will be able to see how long the execution time is for our different writes that we have here. All right, so this should begin writing. And as we see, because these nodes are far apart, we will have a somewhat high execution time with this deployment. One thing that Kanan mentioned in the preferred region demonstration was that it's a nice strategy to have another node in a nearby region to your preferred region, so that we can reach a quorum between those nodes relatively quickly. So that is a strategy worth looking into. So on purpose, I've written 103 records to our database because I wanted to show that for the first 100 writes, we have relatively consistent execution times that we're seeing, because we have 100 values that have been allotted in our sequence cache. But then when we reach the end of our sequence cache, we will see that our execution time is spiking, because we need to actually refresh that cache from the preferred region, which is not nearby to the Eastern United States. So that is pretty much illuminating an issue with sequence caching. And we could imagine an application that is receiving a ton of writes in financial services or an e-commerce application. And this can be quite an issue. So as we see all of the subsequent writes, the two subsequent writes, then are reading back from the cache again. So we could increase this cache value to improve this, but by default, as I mentioned, 100 is the value of our cache.
Yeah, I think it's also important to trade this off with the number of sessions, right? Because if you keep issuing 100 cache values per session, you could like issue a lot of sequences, even though you're not using all of them, right? So,
Yep, totally.
yeah.
Causing gaps in the sequence, or
Lost sequence numbers on failures and all of that.
More overhead on the system as well. Yeah, so now I'm going to run the same simulation just using UUIDs, and I won't even.
So Venkata had a question, which is, couldn't we reload the cache when the cache is half empty or something? Yes, we can, Venkata. We can proactively do that. But I think the reason we choose to not do it is to keep the system simplistic, because you've already amortized the effort of fetching into 1 in 100, right? So, and it usually doesn't show up as much more than a blip. But if it were extremely geo-distributed applications in which you want to smooth this, yes, this is something that could be done.
And this talk isn't just to explain, the difference between UUIDs and sequential IDs, but also to sort of show that distributed SQL means a lot of different things. And the way that you tune your data tier and your distributed database can sort of inform these decisions. Like, this is a little bit of a contrived example. I wouldn't recommend that anyone is actually running a database like this in production, but these are the sort of thoughts that you need to have when deciding how to architect your application. So I will run the same simulation using UUIDs now from the East region. And what we would expect to see here is that we will have no blip in our execution time, because all of these UUIDs are being generated without needing to incur the latency cost of retrieving the next value in our sequence. So I could have run, 100 of these or whatever, but it truly is not necessary, because we can see that we don't have any execution times in the 300 millisecond range, or potentially even higher had we run this from the node in London. So yeah, that is the part of the demo that I wanted to show. And to get back to our slides.
So there's a question from Sridhar. If the caching is per session, wouldn't you end up with out of order sequence IDs across sessions?
Out of order sequence IDs. Yes, you would. Yeah, if it's per session, you would find it to be out of order. If you mean in terms of at the time that the writes are made to the database, then yes, that is absolutely the case. But of course, the IDs will not be duplicated because of the atomicity of the sequence.
I think, and the other important thing to realize, Sridhar, is that you could get gaps and holes in your sequence assignment anyway. Because there could be failures, there could be retries. If there's a failure of an insert after the sequence ID is issued, but before the row is inserted, like a constraint violation, something like that, you would permanently lose that sequence ID, right? So if you have a concurrent set of writes, you could get out of order ordering of sequences anyway. But with this caching, we're just explicitly violating it a lot more in order to get. So because you never had that guarantee anyway, so we're violating it a little more in order to get a lot more performance out of the system.
Yep. So that's it for the demo. I could show, yeah, I just added a slide here on some of the design considerations for Yugabyte, considering that any system will have to be partition tolerant. Yugabyte has chosen to be highly available and strongly consistent. And we're using the Raft consensus algorithm to ensure that all of the data in our cluster is properly replicated and our leaders are being elected with a quorum between the nodes in our database. So these are a couple of terms for people who are new to distributed SQL. You'll want to look into these to have a better idea of what's happening and how these things are being achieved. So with that.
Awesome. Fantastic. Thank you. This was a really neat demo. Really nice to see the real setup and, what happens when you query it from different places and the 101st query bumping up. This is a fantastic, visualization. So thanks a lot, Brett. Once again, we're at time, folks. So if you have questions, feel free once again to drop your questions into the LinkedIn comment box or join our community Slack, yugabyte.com/Slack, and head to the YFTT channel. Brett will answer your questions there. Sumit says, nice demo, Brett.
Thanks a lot.
Agree. So,
appreciate it.
So, all right. Thank you, folks. Makita, thanks you for the talk. Thank you. Thank you, folks, for attending. Thank you, Brett. Join us next week, once again, same place, same time for, another session of YFTT. Until then, see you guys.